Dark openings, some of the most baffling and mysterious phenomena in the universe, continue to capture the imagination of space experts and physicists around the world. These cosmic giants are defined by their immense gravitational pull and their total absence of light, creating a boundary beyond which the known laws of physics simply cease to operate. First predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, dark openings remained purely theoretical concepts for decades. It wasn't until technological advancements in the 20th century that scientists were finally able to gather indirect evidence proving their existence, changing our understanding of the cosmos forever. The turning point arrived during the 1960s when astronomers studying the Cygnus constellation stumbled upon something extraordinary. They observed a brilliant blue star emitting powerful X-rays, behaving in a way that defied traditional explanations. This star appeared to be locked in a strange dance with an invisible companion, drawing intense scientific interest. Further investigation revealed that it was caught in the gravitational grip of a massive dark opening. This discovery, named Cygnus X1, marked the first clear observational proof of dark openings, sparking a new era of exploration and fascination with these cosmic enigmas. Located roughly 6,000 light-years from Earth, Cygnus X1 possesses staggering properties that continue to astound researchers. Its density is so extreme and its gravitational pull so strong that not even light can escape from it. This ultimate characteristic earned these objects the now famous title of dark openings, representing the very essence of their terrifying mystery. Since the discovery of Cygnus X1, astronomers have uncovered numerous dark openings scattered across the universe. Current estimates suggest that our Milky Way galaxy alone may harbor over 100 million of these hidden giants, even though detecting them precisely remains a formidable challenge. Despite their elusive nature, scientists have made significant progress in identifying various types of dark openings within our galaxy. These range from stellar mass dark openings, born from the remnants of massive stars, to the supermassive ones that dominate the centers of entire galaxies. The gravitational influence of dark openings extends far beyond their immediate surroundings, shaping the evolution of cosmic structures and determining the fate of any nearby matter. Objects that stray too close are mercilessly drawn towards the event horizon, the ultimate point of no return, where they experience forces beyond human comprehension. Once an object crosses the event horizon, it is subjected to extreme tidal forces that stretch and pull it apart in a dramatic process known as spaghettification. This haunting phenomenon results when the gravitational gradient across an object's length becomes so intense that it stretches into a long, thin filament resembling a strand of spaghetti. The incredible forces at play overpower the object's internal bonds, tearing it apart and sending its remains spiraling into the singularity at the core of the dark opening. This singularity, a region of infinite density, remains one of the greatest mysteries of modern physics. Even though dark openings present an irresistible allure as natural laboratories for pushing the boundaries of physical theory, they continue to cloak themselves in layers of mystery. The mission to unlock their secrets is relentless, fueled by humanity's insatiable curiosity about the fundamental workings of spacetime and gravity itself. Despite the vast distances that separate us from these phenomena, the nearest known dark opening being about 1,500 light-years away, concerns and questions about their influence and potential risks remain topics of intense debate among researchers. In 2019, scientists achieved a historic breakthrough by capturing the first-ever clear image of a dark opening. This achievement focused on the supermassive dark opening at the center of the galaxy M87, known as M87 star. This monumental effort, carried out using the Event Horizon Telescope, provided humanity with its first visual evidence of a dark opening structure. The captured image revealed intricate and surprising features, challenging earlier notions that dark openings were merely voids of empty nothingness, and offering crucial insights into their complex internal architecture. Through meticulous image analysis and processing, scientists discovered that a dark opening consists of 3 distinct layers. The outermost layer is the event horizon, the critical boundary beyond which escape is impossible. Once an object crosses this line, it is inevitably pulled inward with no chance of return. Moving closer to the center, the second layer emerges, the photon sphere. This is a strange region where light itself orbits the dark opening, trapped forever in a relentless gravitational dance. Here, even photons, the fastest particles in the universe, find no escape from the dark opening's overpowering grip. At the very core of the dark opening lies the singularity, the final and most mysterious layer. In this place, matter is crushed into a point of infinite density, where the known laws of physics collapse and reality itself begins to break down. Within the singularity, familiar concepts of space, time, and even causality may cease to exist, plunging scientists into a realm of deep theoretical speculation and uncertainty. This unfathomable core remains one of the ultimate frontiers of human understanding, and its mysteries continue to elude even our most advanced theories. Despite the shared three-layer structure, dark openings exhibit a wide variety of individual characteristics that make each one unique. Their mass, spin, and charge can vary, producing different behaviors and effects that defy easy classification. Traditional scientific methods often prove inadequate when it comes to studying these colossal entities, forcing researchers to develop new and innovative approaches. Since direct observation is impossible due to the immense gravitational barriers, scientists rely on indirect techniques, studying the effects of dark openings on nearby stars, gas clouds, and radiation patterns to unravel their secrets. Any attempt to send probes directly into a dark opening would be futile. The extreme forces at the event horizon would crush and destroy any spacecraft long before it could transmit useful data back to Earth. Nevertheless, scientists remain undeterred, pressing forward in their quest to better understand these cosmic phenomena. Various theories have been proposed to explain the origins and behaviors of dark openings, ranging from the collapse of massive stars to complex cosmic dynamics involving the earliest moments of the universe's formation. One particularly fascinating investigation involved studying the center of the M87 galaxy, where a supermassive dark opening holds sway over an entire galactic region. NASA's careful observations have revealed the immense gravitational reach of this dark opening, offering tantalizing hints about the nature of these giants and their role in the broader cosmic order. Although much remains unknown, each new discovery brings humanity one step closer to deciphering the profound mysteries of dark openings, promising to reshape our understanding of the universe itself. Adding to this fascinating journey, Roy Kerr's groundbreaking work in 1963 introduced an entirely new perspective on dark openings. He proposed the idea of rotating black holes, forever altering the scientific view of these enigmatic objects. Central to Kerr's model was the concept of the ergosphere, a region surrounding a rotating dark opening where spacetime itself is dragged around by the object's rotation. In this strange domain, the balance between gravitational collapse and centrifugal forces creates new possibilities that challenge traditional physics and hint at even deeper mysteries concealed within dark openings. Perhaps even more intriguing is Kerr's theoretical prediction of the existence of Einstein-Rosen bridges, commonly known as wormholes. These hypothetical structures could serve as shortcuts through space-time, connecting distant regions of the universe or even parallel universes. The idea stems from the way massive objects warp the fabric of space-time, as described by Einstein's general relativity. Wormholes could, in theory, create a bridge between faraway points, allowing rapid travel across unimaginable cosmic distances. Yet despite the seductive possibilities, the practical stability and existence of wormholes remain hotly debated topics within theoretical physics. While the concept of wormholes stirs dreams of interstellar travel and cosmic exploration, the reality remains elusive. The extreme conditions required to stabilize a wormhole, such as exotic matter with negative energy density, have yet to be observed or created. Nonetheless, the pursuit of this idea continues to inspire scientific inquiry and imagination. If one day humanity can unlock the secrets of wormholes and dark openings, it could open the door to a future where distances between stars and galaxies become traversable, transforming our place in the cosmos forever. Interstellar travel and the exploration of time sound incredibly exciting, but in reality, they come with some major challenges and limitations that bring these fantastical dreams back down to Earth. One of the biggest issues is the intrinsic instability of wormholes, which, when combined with the overwhelming barriers created by quantum forces and deadly radiation, casts serious doubt on their practicality as real-world modes of transportation. On top of that, Einstein's theory of general relativity sets strict limits on how fast anything can move through spacetime. So even if wormholes could somehow be stabilized, they might not actually allow faster-than-light travel, the very thing that countless science fiction stories dream about. Despite these serious obstacles, wormholes continue to capture the imagination of scientists and dreamers alike, serving as an endless source of curiosity and exploration into the deepest mysteries of the universe. One fascinating idea that continues to intrigue physicists is the concept of the SWW wormhole, named in honor of the pioneering scholar who first proposed it. This idea captures the imagination by suggesting the existence of cosmic portals and alternate realities that could, in theory, be reachable. These bold concepts inspire humanity to constantly rethink the boundaries of our universe and wonder about the infinite possibilities that might exist beyond our current understanding. At the center of these efforts is the relentless pursuit of a theory of everything, a single unified framework that would reconcile the seemingly incompatible worlds of gravity and quantum mechanics, two forces that currently operate under very different rules in physics. Standing at the forefront of this monumental quest is the renowned theoretical physicist Michio Kaku. His groundbreaking work has significantly advanced the study of superstring theory, one of the most promising candidates for a theory of everything. Superstring theory marks a dramatic shift from the traditional way we think about matter and particles. Instead of imagining particles as tiny, point-like objects, this theory proposes that the most basic building blocks of the universe are actually tiny vibrating strings. Each of these microscopic strings vibrates at different frequencies, much like the strings on a musical instrument, and these vibrations give rise to all the different particles and forces we observe in the natural world. In this new paradigm, the entire universe resembles a grand cosmic symphony, where each particle represents a unique harmonic resonance of these fundamental strings. One of the most astonishing ideas to come out of superstring theory is its potential to explain mysterious phenomena like dark openings, wormholes, and other exotic solutions to Einstein's equations of gravity. As these tiny strings move dynamically through space-time, they can create gravitational singularities and bizarre topological anomalies, hinting at the existence of structures and phenomena far beyond what we can currently observe or understand. However, the elegance of superstring theory hides an incredible complexity. In order for the math to work out, the theory requires the existence of additional spatial dimensions, far more than the three we experience in everyday life plus time. These extra dimensions are hidden from direct observation, making them incredibly difficult for human intuition to grasp. To help illustrate this concept, physicists often use the analogy of fish living in a two-dimensional lake, unaware of a third dimension above and below them. Similarly, these hidden dimensions could be compactified or curled up so tightly that we can't perceive them at everyday scales, yet they still profoundly influence the structure of the universe. Although we can't directly observe these extra dimensions, their theoretical presence offers a powerful way to explain many complex structures and strange anomalies seen throughout the cosmos. Moreover, the intricate mathematics underlying superstring theory has led to a renaissance in mathematical physics, uncovering deep connections between dynamic mathematical patterns and real-world physical phenomena. This union of mathematics and natural science has opened entirely new avenues of thought, highlighting just how interconnected these disciplines truly are. Despite its stunning beauty and scientific potential, superstring theory remains largely untested. Its reliance on hidden dimensions and energies beyond current experimental capabilities relegates it, for now, to the realm of mathematical speculation. Yet the bold vision it offers continues to ignite the imaginations of researchers and enthusiasts around the world. Humanity remains drawn to the challenge, inspired to push deeper into the unknown, guided by the light of superstring theory, standing on the threshold of a new era of cosmic understanding and enlightenment. The challenge of unraveling the mysteries behind quantum dark openings, better known as black holes, has been one of the greatest puzzles in physics for decades. Despite the relentless efforts of countless physicists, a complete solution has continued to elude us. This immense difficulty led Edward Witten of the Institute for Advanced Study at Princeton to famously describe superstring theory as 21st century physics that accidentally fell into the 20th century. But there is renewed hope. In recent years, several independent research teams have reported breakthroughs suggesting that string theory might indeed offer a solution to the black hole puzzle, although so far only in a simplified two-dimensional context, not yet within the full 10-dimensional framework envisioned by traditional superstring theory. While this new development marks a promising step forward, it also underscores just how complex the full picture remains. The quest for a complete understanding is ongoing, and the obstacles are formidable. Still, the very search pushes us ever deeper into the most mysterious corners of the cosmos, where reality and theory intertwine, and the secrets of existence await discovery. Studying black holes not only challenges our notions of what is real but also forces us to confront profound questions about the nature of life, matter, and the universe itself. One particularly fascinating area of study is the interaction between black holes and other astronomical phenomena like neutron stars and gamma-ray bursts. These interactions reveal intricate and sometimes violent processes happening on scales almost beyond human comprehension. As black holes merge, collide, and consume surrounding matter, they create gravitational waves, ripples in the fabric of spacetime itself. These waves propagate outward, carrying valuable information about the massive, energetic events that created them. Thanks to groundbreaking instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, which made the first direct detection of gravitational waves in 2015, we now have a brand new way to study the universe. This revolutionary discovery has opened up a whole new era in astrophysics, allowing scientists to observe violent cosmic events like never before. As LIGO and other observatories continue to record gravitational wave signals, we're getting clearer and clearer pictures of how black holes form, evolve, and interact with the universe around them. But many mysteries remain. One of the most puzzling is what happens to matter as it falls into a black hole. According to current models, matter is stretched and compressed by the immense gravitational forces as it approaches the singularity. Yet a major paradox remains: the fate of the information contained within that matter. This mystery is known as the information paradox, and it strikes at the very heart of quantum mechanics. According to quantum theory, information about a particle's state can never truly be destroyed. But black holes seem to violate this principle, appearing to completely erase any information about the matter they consume. This contradiction challenges our entire understanding of physics, and finding a resolution to the information paradox remains one of the biggest goals in modern theoretical research. Adding even more layers to this cosmic puzzle is the idea that black holes might play a much bigger role in shaping the universe than we once thought. Some theories suggest that supermassive black holes at the centers of galaxies actually drive galaxy formation, influence star creation, and even impact the growth of planetary systems. And when you combine that with the mysterious forces of dark matter and dark energy, two substances that make up the majority of the universe but remain largely invisible and unexplained, the possibilities become even more intriguing. Understanding how black holes interact with these hidden components of the cosmos could be the key to unlocking some of the universe's greatest and most elusive secrets.